It's just astounding. Yeah, the dynamics of orbiting objects are really harshly oppressive on things that do not orbit in the elliptical plane. Those things get weeded out quite quickly. When I was teaching astronomy, this was my favorite lesson to do when I had someone coming in to evaluate me. Because everyone's fascinated, and we would really quickly get hip deep in the mathematics and science of it all. And the students really enjoyed it, but the administrators, their eyes would kind of bug out and roll back in their heads. And they somehow thought after watching me that I knew lots of science because the lesson was just amazing. I would get comments, I really didn't understand it, but it sounded amazing. But
sounded amazing.
Yeah.
Like it sounds amazing.
It's something, I think if you talk to people about what's your first memorable astronomy experience, the first time you looked through a telescope, there are really two things that come up. The moon and the rings of Saturn are two really awe-inspiring, life-changing, thunderstruck sort of observations that people...
For sure.
And
Jupiter too. I would put that
Jupiter too
category. Just
Jupiter in that category as well.
Yeah.
For me, Saturn was view of Saturn was what set me on the path more than 50 years ago. The local village priest, his son and I went to school together, and Father Bassett had this, I thought it was gigantic telescope in his office. I think it was probably one of the old Japanese Tascos, F12 or something like that. So it was a long telescope on a beautiful wooden tripod. I pestered him for months. I was merciless. And my friend would like, would you quit bugging my dad? I'm like, no, he just has to take me out. And so one nice summer night, he invited all the neighborhood kids. And come on, let's set up the telescope. Let's look at the moon. Let's look at some other things. Most of the neighborhood kids got tired of it after about half an hour. I stayed. I was out there for a couple of hours, and he eventually showed me how to run the equatorial mount. And I'm like, what's this one? What's that one? And I like, wow, that one's bright. It's kind of yellow. What's that? He said, well, you know how to point the telescope now. Go ahead and have a look. And it was Saturn. And I could see the rings. And 50 years ago in northern Illinois, southern Wisconsin, the light pollution wasn't too bad, not like it is today. And I just remember being absolutely floored by the view, and immediately set off pestering my parents to buy me my first telescope for Christmas.
Yes.
Which I got. I got a nice little 60 millimeter Tasco. One of the ones that the older it is, the better it is, right? They kind of deteriorated.
Well, the Tascos back then were made in Japan.
Right. You know, back then they were made in Japan, and the optics were quite nice.
Oh yeah.
And I lived in town in an apartment over a shop. And so I went out on the fire escape and went and filched a ladder from my grandmother who lived a couple blocks away. Carried the ladder all the way up the fire escape and used it to drag my telescope up onto the roof of our building.
Mm-hmm.
And then it was right face to face with a streetlight. So I pulled up the ladder and I tipped it over the alleyway, about 8 foot wide, because the next building was a little higher. And I took my telescope under the arm and crawled across the ladder and set up behind the parapet. This is nice. I'm not bothered. And I was enjoying the moon and various things. And then my mother realizes I'm not in the house, and where's Danny? And my brother blew the gaff. He said, he's out on the fire escape with his telescope. And my mother just went ape. And then she went out and I wasn't there. And then, where are you? I'm up here. I think it was spring before I got to use my telescope again. I didn't care.
You didn't care.
Glorious, and changed my life forever.
Mm-hmm.
New NASA research indicates that Saturn's iconic rings are not only younger than previously thought, but also that these rings are actually disappearing at an extremely fast pace. The research found that the rings are draining away toward the planet as a dusty rain of ice particles. Saturn's rings consist mostly of water ice that ranges in size from microscopic dust to large boulders. Ultraviolet light from the sun and plasma clouds coming from tiny meteoroid strikes charge the icy dust, which then becomes bound to Saturn's magnetic field and pulled into the planet by gravity. This material rains into the planet and begins to disintegrate, allowing it to react chemically with the electrically charged part of Saturn's upper atmosphere, the ionosphere. The ions glow in an infrared light as part of this process if the rain is light, but the emissions dim if the rain is heavy. This was observed using instruments attached to the Keck telescope in Hawaii. The rate of disappearance in this ring rain study has allowed scientists to infer that Saturn's rings formed less than 100 million years ago. This means Saturn wasn't born this way, as the planet is known to be over 4 billion years old. And when the ring rain data is combined with observations made by the Voyager 1 and 2 missions, scientists from NASA Goddard are able to estimate that the rings will be gone in 300 million years. So if this rain doesn't go away, Saturn will be ringless another day.
Well, hello, everybody. It's Scott Roberts and Dr. Daniel Barth here from both of us here in Northwest Arkansas.
Yes.
And it's our pleasure to bring you the 13th episode of How Do You Know? Okay, which is awesome. We have, if you look at the description, the text description here in this post, you'll see a link to the study guide if you want to download it. It's very, very nice. And Daniel, you're going to talk about the forces that kind of keep everything either in check or can destroy things. So
yes,
right.
Absolutely.
So that's awesome.
This whole adventure of the activities, I learned so much as a teacher from my students' questions. It's one of the most wonderful things about my job. And quite a number of years ago, a student asked, well, where do the rings come from? And this would have been in the late 80s. And this set me off. There was no Google, no Siri. So this set me off on quite a quest to figure out when. Back then, people thought they knew, but they weren't as certain as they are today. And when we go back to the rings and the history of the study of the rings, we go back to names everyone recognizes, but not necessarily as people. It's kind of funny. Cassini, if you say Cassini today, people think of the gap in the rings. They don't think of the French astronomer who studied from the observatory in Paris. If you say Roche Limit, people don't think of Edouard Roche. And pardon me to any of our French-speaking viewers, I'm sure I'm butchering
the name.
And I don't want to try to sound French. That would be even worse. So we'll just say Edouard Roche. And it goes back all the way to James Clerk Maxwell. And Professor Maxwell was the one who, in fact, theoretically proved. Then the question came ever since, I think, Huygens had the first good view of the rings in a 6-inch reflector. And then the immediate question, well, what are they made of? And Maxwell stunned everyone by proving that the rings could not be solid or liquid or gas. And people were like, stop.
What else
what's
is
it made
there?
of? What's it made of? And essentially what Maxwell understood, he knew by that time, people were quite certain that at some point the atmosphere ended and space was a vacuum. And he said, well, liquid, if we take pumps and we pump the air away from liquid, it starts to boil. If we have gases in a vacuum, they disperse. Because we know gases in higher pressure, lower pressure, they tend to expand to fill their container. So Maxwell said, well, it can't be liquid, it can't be gaseous. And people for a long time had thought that the rings were some kind of fantastic solid surface. And Maxwell said, no, this can't be so. And it has to do because of certain forces that are there. And I've got some illustrations today, Scott, and I think they will help us out. So I'm going to pop some up and share a screen with you and we'll talk about them. So this is something that Maxwell proposed. And what Maxwell figured out is if you had something spinning, there's two kinds of forces going on. First of all, and I think you can see this if you take a look. I've got my little baseball from last week's Tides episode. And if you spin that, you think about spinning, the Earth spinning in place. Well, if you went up to the North Pole or to the South Pole and you just stood there, it would take you 24 hours to make one rotation. It's a very slow spin, and yet at the equator, we are moving at over 1,000 miles per hour, about 1,600 kilometers an hour. And so we start to think about this and we realize, even though the entire Earth is effectively solid, spinning is one piece, not all pieces move at the same speed. If you think of a flat disk, like an old, I used to use an old LP record for this, but I don't have them anymore. But if a flat disk is spinning, the linear speed, as you go farther out from the center, the linear speed gets greater. And so essentially two layers, one's moving faster than the other. And this creates what's called shear forces, where two things are trying to pull apart this way. The other thing, of course, is that everything has inertia. And when something is rotating, if you've ever been a kid and spun something around on a string and let it go, basically everything wants to continue flying in a straight line. And it requires, if you think of a ball on a string and you're spinning it, that string is actually pulling in toward the center, what we call a torsional force or a centripetal force. And so with something as big as the rings, they're 280,000 kilometers wide. They're amazingly big. Those pieces on the outside, if it's all spinning at one rate, Maxwell said there's nothing we know of that would withstand the centripetal forces. It would rip itself apart. The shear would break it apart. He said the rings have to be particles. They can't be anything else because nothing else would hold together under this enormous scale and strain. And so Maxwell comes up with this idea and he says, gee, the rings must be rotational. Well, that's great. And you think about that and that's okay. But when we think about this, and I'm going to stop the share here for a second. When we think about this, and again, you can see this if you take a baseball, and I'm holding this, I think, let me adjust my camera. You can see the top of this. As it spins, the center spins relatively slowly, whereas the outside spins really quite rapidly. And so we've got this thing, and you say, okay, well, gee whiz. So the rings rather cannot be solid, they cannot be liquid, they cannot be gas. So where do we go from there? And if we think about that, and we start to think about planets and moons, well, okay, so we know moons are particles, but how did they get that way? Another interesting question that came up from one of my classes is a student said one day, well, can you put a moon anywhere you want? I said, well, what do you mean? And they said, well, if it was really, really close, the gravity would be enormous and you would have these enormous tides. And wouldn't that be a fantastic thing to go see on some other planet, not ours? And he said, and could you have a moon that orbited like a light year away? And so I thought about this, and this also led me back to the Roche limit. Roche is the first one who says, no, you can't put a moon anywhere you wish. Furthermore, as we will see on our episode next week, not only can't you put a moon anywhere you want, but it doesn't matter where you put it, it's not going to stay there. It's going to either spiral in or it's going to spin away. And so the distance between any planet and its moon is never stable. It's always changing. And so you get this, it starts to sound like it's a very complex mix of factors. But the other interesting thing when we take a look at moons and why moons that wander too close get destroyed, that's essentially what the Roche limit means. There is a point as a moon spirals in towards a planet, my head being the gas giant here, and if I have a baseball moon orbiting my head, as it spirals in closer and closer, my head doesn't have very much gravitational pull, but Saturn, Jupiter, and other planets do. I will have an innermost limit where at some point the planet's gravity will rip the moon apart. And again, I'm going to rely on a couple of pictures here. And I think I want to make sure I'm getting the right ones. Yeah, okay. So let's take a look at this again. I'm going to share the screen once more. And I'm hoping everybody is finding these diagrams useful and fun. But let's think about a moon in orbit around a planet. One of the things we don't think of very much, gravitation is very sensitive to distance. We know about the inverse square law and all of this, but if you get twice as far away, gravity shrinks to 1/4. 10 times far away, gravity is just 1%. So gravity is very sensitive to distance. When we have a relatively large moon of a couple hundred kilometers or better, that's not terribly large, but we get this situation where the near side, our planet being the big blue crescent here, the near side experiences a lot more gravitational pull than the far side does. And if you think about that, that's very much like having a ball of clay or something and holding it on to it from one place, and it slowly starts to stretch and droop just from gravity. And if we think about that, as a planet or a moon gets closer to a planet, gravitation is going to take it from a round shape and it's going to be stretching it now into an elliptical shape. So if we think about this, and let's see if I can, why am I not able to change? Oh well, we'll take a look at the next one. Here we go. Here's a lovely illustration, and if you're admiring the artistic skill of these, yes, I did them all on Microsoft Paint. So if you love them, it's me. If you hate them, it's me. But essentially, if we think about a moon getting closer, and I've drawn simply 3 positions here, you can see in the outer position, position 1, the moon's essentially round, assuming it's big enough to be a sphere. As it gets closer, it stretches a little, but as it approaches the Roche limit, tectonic fractures begin to occur. The crust of the moon begins to break up. And we get the case of Jupiter's moon Io. Well, Io is in an elliptical orbit. And so what's happening? As it comes towards Perigove, what's happening is, here we are. Here's a lovely, and let's make this a little larger for our friends. There we are. So as Io comes in here towards Perigove, and the Roche limit here is the nice red ring, as you come in towards Perigove, Io is actually stretched. Imagine the kind of force it takes to take a 3,000 kilometer wide moon made of rock and just stretch it. And we're talking a stretching of 8 to 10%. So it's not insignificant. This is not a little 3 centimeter Earth tide that our moon creates as it passes over the continents. This is a substantial distortion of shape. And then as it travels back to apogee, terms like perigee, apogee refer to Earth, of course, perigee, apogee refer to Jupiter. And we have perihelion, aphelion for planets around the sun, just a little terminology for you. So we have perigee, P for pretty close, apogee, A for far away. And as it comes back here, it relaxes into a circular shape. Stretch, relax, stretch, relax. And Io's orbit is only it's less than 2 days. So it does this about something ridiculous, like every 15 or 20 hours, it stretches and relaxes and stretches and relaxes. And Scott, I don't know if you've ever been a fidgety person. I always was. You take and sit and take a paper clip and bend it back and forth and back and forth.
Oh,
and
yeah.
back and forth, and eventually it breaks. And at some point, if you do this as a child, you realize touching that end where it's just broken, it's hot. This flexing adds heat to the metal because there's internal friction as the layers slide over each other. Much the same is going on worldwide on Io as it stretches and relaxes. And this creates a tremendous amount of internal heat, which has liquefied the mantle. Not only that, but this stretching and relaxing, you can imagine, it's kind of like squeezing a water bottle or a ketchup packet. It puts a lot of pressure internally. And so Io is the volcanic theme park of our solar system. More than 450 volcanoes known. We suspect new volcanoes get created quite regularly. I'm sure do you remember I think it was 78, 79, Voyager flew by and Carl Sagan coming on the news and saying, oh my gosh, this is so amazing. Look, you can see a volcanic plume over the edge of the disk of Io. And it didn't take very long for people to realize, gee, either we got really, really lucky seeing a volcano right there, poof, over the edge, or there's just a lot of them. And it was flybys, and the Galileo mission mapped Io pretty thoroughly. And it's a terrific volcanic wonderland. And most of the volcanoes there erupt sulfur and sulfur alloys. And so Io is wildly colorful. Go ahead and look up some images on your favorite search engines, friends. Io is just, it looks like a weirdly frosted Halloween treat. It's amazing. Kind of like a pizza, I guess. So you've got this situation where things are stretching and pulling apart. But the question still comes, well, gee, how in the world is that gravity strong enough to pull apart a moon? And you think, okay, well, if it's a rocky moon, and I said I went out and got some things. So here's a chunk of stone. I live up on a mountaintop, so there's lots of rocks around my place. And so I found this nice chunk of, I'm not sure if this is, I think this is metamorphic rock.
Limestone, maybe?
It could be a limestone. Yeah, it could be.
Yeah.
And that would be metamorphic, would it not? Sedimentary and then heated up to become limestone? I'm struggling. We need our good friend, Dr. Catherine Auld, who knows a lot more geology than the two of us. But we've got a piece of limestone here. And this is solid. And if you think about, oh, I'm going to hang this and watch it stretch. Well,
it is a sedimentary rock. That is a sedimentary.
It's sedimentary? Okay,
yes.
There we go. And we'll assume that this is one.
Okay.
I'm sorry, I'm not that kind of doctor. But I try to flex this and I'm like, no, this is rigid. And in fact, it's rigid because it's held together by chemical bonds. There are atomic forces binding the particles of this rock together. And so it's hard, it's rigid, it's a classic crystalline solid. And frankly, breaking it takes some substantial effort. Could I break this? Yes, I've got a 3-pound sledge somewhere out in the garage, and I could set it on a tree stump and give it a good old whack. And I'm sure I could break it or certainly chip pieces off, but it's not going to fall apart very easily.
Right.
Moons and planets aren't made like this. When we talk to people and we say, oh, Earth is a rocky planet, the moon is a rocky terrestrial body, so is Mars, blah, blah, blah. And you think, oh, well, it's solid stone. Oh, yes, well, we intellectually know that there's layers inside. The mantle is molten and the core has molten and solid layers and yada, yada. But we think of Earth as a stone. It's not. It's not. Our moon isn't either, nor are any of the moons. And so you say, okay, well, Doc, if it's not a rock, it's a rocky planet, but it's not a rock. You kind of get to like you're feeling like you're talking to Maxwell again. Okay, what is it? So I have another lovely example from my driveway. I have some gravel. So if I grab a handful of gravel and I hold this, yes, I can hold it. But if I release it, it falls apart and pieces fall on my floor and go under my desk. Yay. And you say, well, of course they do, Dr. Barth. They're not attached. But in fact, Scott, they have mass, and so they must have gravity.
Yes, right.
However, Earth's gravitational field overwhelms the tiny, tiny gravitational forces between the stones. And so if I release them, they simply fall apart. And if I had a handful and threw it up in the air, they would all fountain out into, did you ever play that game when you were a little kid? Go take gravel and throw it up. Yay. A lot of little kids.
You throw gravel?
Oh, yeah. We were poor growing up.
We threw rocks at each other, I think.
Yeah, we threw rocks at each other. But
Yeah.
if you take some pea gravel and you have a handful and you throw it up, it won't stay together. And
No.
people are like, well, duh, of course not. It's separate stones. Well, all that's holding the separate stones of the Earth and the Moon together is their mutual gravitational attraction. If you think about Mars, which perhaps it has some liquid mantle, but is essentially geologically dead, frozen planet. It's all one piece. You think about Mars and you think, oh, Mars is a solid. No, it's not. It's a very large pile of rock that's it has enough gravitational force that it's held together coherently and shaped itself into a sphere. But it's not a solid piece. So when we think about why do moons fall apart? Well, when the gravitational force nearby is just a little bit stronger than the gravitational force holding them together, then the pieces fall apart and become separate again. When we think of a Roche limit, what we're actually calculating is how close do you have to be? Again, I'll use my head as the gas giant. It's a very appropriate prop. And here's our baseball moon. So there is some distance when the attractive force between the surface of the moon and I, and the self-attractive force that's holding the moon together, as I'm getting closer and closer, those forces are becoming more equal. And at some point they become equal. And then if you move any closer, the gravitational force of the planet pulling things apart is stronger than the self-gravitational forces holding them together. And the moon is literally shredded into pieces. Now, we think about this and you look at a handful of gravel and a stone and you go, oh, okay, that makes sense here. But very few of us get to experience a different gravitational environment than this one we're born in. Very few of us. There's a handful of people who have been to the moon, and not all of them are still with us. There's a very small club that have actually been into orbit and experienced microgravity. But even if you were to take this handful of stones in microgravity and release them, so I can't do this obviously here, but they would float together. But if you started traveling closer to the Earth, at some point, the Earth's gravity would be greater than their self-attraction and they would start falling separately. And this is essentially what the Roche limit is. It's that point where the pull from the planet is just as great as the self-attraction of the pile of rocks that we call a moon or an asteroid holding it together. Now, if you get things that are small enough, look, here's one now. This is small enough piece that the forces holding it together are atomic. chemical bonds. Well, you say, how much stronger are chemical bonds than gravitation? What people don't realize is that gravitational forces are, in fact, the weakest forces on the planet. And I can demonstrate that pretty easily here. I have with me, I have a nice magnet, and I have a steel washer from out in my garage. And if I hold this here, and I've got this magnet. Now, Scott, what's holding the washer onto my palm? Why is it
Gravity.
resting? Gravity. And so I bring this magnet down, and I don't have to get very close. And there we go. This little magnet that I'm holding in my hand has now defeated the gravitation of our entire planet. 12,000 miles wide. Essentially, the Earth is 1 mole of kilograms. That, for our chemistry friends out there, if you know how big a mole is, it's crazy. 10 to the 26. And this little neodymium magnet, and it wouldn't take something this big. You can pick up a paperclip with a weensy little, rubbery ceramic fridge magnet.
Sure.
And you're like, ooh. And kids do that all the time. That's one of the fun things as a kid. Do you ever get magnets as a present as a kid? Ooh, your parents got you the magnet science kit? I did.
Mm-hmm.
And you're like, ooh, what sticks to the magnet? Oh, how much can I pick up? How many paper clips can I hold? All these things. But you don't realize, my little magnet is overcoming the gravitational force of the entire Earth. Gravity is the weakest of the fundamental forces of nature. How much weaker? Electromagnetic forces that form chemical bonds. Those electromagnetic forces are something ridiculous, on the 40 orders of magnitude bigger than gravity. You go, 40 orders of magnitude. Well, what's that? Every 12 is a trillion, right? So how many 12s go into 40? At least 3. So it's like a trillion times stronger. And at some point, you sound like a couple of 7-year-olds arguing about how much stronger Superman is than Spider. Oh, a trillion times bigger. It's really stronger. And it's such an enormous gap.
So someone is commenting here, and Ben Crosswaite says, so why hasn't Jupiter's moon or the Earth's moon not already broke up and started making rings?
Okay. For that, it turns out that the Roche limit occupies a particular place in space. And yes, we're going to go there. We're going to give you a little math today. Math is happy, math is fun, and some people think I'm nuts. But here's the equation for the Roche limit. Now, what we're looking at here, what's important? The masses of the moon and the planet don't matter. They don't occur as terms here. The radius of the planet does, and then D1 and D2 are densities. How dense is this? How dense is the planet compared to the moon? And then it's a cube root function. That's what the 1/3 power means. But this isn't a terribly complex equation. There are only 3 terms in it: the radius of the planet, the density of the planet, and the density of the moon. And you pop it in and you'll get a definite distance. And if we take a look at a picture of Saturn with its rings, hey, voila, presto. The outer diameter of the rings is exactly where the Roche limit of Saturn lies. Precisely where it lies. So with the accuracy that we can calculate. Now, it does matter. How strong are things? If you have a moon that's icy, ice is quite weak. You can break ice more easily into pieces. So surprise, guess what? Icy moons get shredded at a farther distance. If you have a moon that's made of stone, stone is a little bit more rigid, a little stronger, and a pile of stones is more massive, more dense, generates more gravity. So guess what? A rocky object can come in closer than an icy one before it gets destroyed. And if you had a metallic body that was all chunks of metal, I can't quite imagine this. There may be some asteroids that are like this. But if you had something that was all chunks of metal, it would be about twice as dense as stone, roughly. And something like that could get even closer to a planet. So the answer is simple. Our moon is not close enough. The Earth's Roche limit is, I'm trying to remember from calculations I've done, 65 or 75,000 kilometers out. And our moon is about 385 kilometers out. And it's going farther away each year. So our moon is in no danger. Jupiter's moons, in fact, all the major ones, all orbit outside the Roche limit of Jupiter. Io, as we mentioned, flirts with it. Io flirts with it, and we see the disruptive effects of, we see tectonic fractures and volcanic rifts and volcanoes and all sorts of active things on Io. And so it turns out that your question is a very good one, but that Roche limit lies in a particular place, and it has to do with the density of the planet, the density of the moon. And you can calculate, and basically if you come too close, it's like going too close to a black hole. We talk about the spaghettification, right? People talk, what happens if you fall into a black hole? People say, oh, the tidal effects will stretch you and rip you apart. This is the Roche effect. This is absolutely the Roche effect. And neutron star, I imagine, would do the same thing to you. Not that I'm going to try it, but it would stretch you. And so we get this. So we have this interesting intellectual concept, and it's great. But let's take a little bit more practical step and say, gee, how do we demonstrate this if we're talking about a classroom or an outreach situation? How do we demonstrate this? Turns out it's not that hard. The idea is, with the difference in force between the near side and the far side, right? So the ball is being stretched, and I've got some clay here. That's I've softened it up. So if the difference in force between the near side and far side is great enough, it begins to stretch, and it begins to stretch out and becomes more oblong than circular. And eventually, the stretching simply becomes great enough that pieces get torn away. The internal gravitation is weaker than the planet's pull. So essentially, something falls apart under its own weight. We used to have word problems like this, and my physics teacher used to love them. Oh, if you have this giant spool of string that's this diameter and has this linear density, and you fly up in a helicopter and you start unrolling the string, how far can you unroll it before it snaps? In other words, how far out, how much string can you unroll out of the helicopter before it parts under its own weight? So what I did, Scott, is I've got an activity. You just need a ball of clay that's about 3 centimeters. This is plenty of clay. And what we can do is we can roll this out into a cylinder. Well, if we're patient and careful, we can actually roll this out into a clay string. And let me see if I can do this for you here. What I have here is an empty soup can. And yes, I rolled out a clay string, and I did as best I could to keep this to a 3 millimeter diameter.
Okay.
Now, I suppose if I had some kind of hydraulic press and the right kind of die, I could extrude myself a 3 to 4 centimeter string of clay. But what we find is that clay, if you think about it on the microscopic level, clay's like our pan of gravel. The particles inside are not connected like a crystalline rock. They're simply particles caught in a matrix. And so clay is actually an excellent analog for our moon of pieces of rock or pieces of ice that are held together by their own gravitational pull. Here they're held together by surface tension forces because the clay particles are suspended in oil, but no model is perfect. And what can you do, Scott? You can take this and start unwinding it. And I cheated today for the show. I made a weak spot where I knew it would break. Actually, when I went and tried this with a very nice smooth string of clay, and I did it over my stairway. And I said to my wife, keep the dogs off the stairway, and I started unrolling clay. and I came out to a string about 53 centimeters long, about half a meter of clay before it broke. As the clay string gets thicker, you're able to unwind more. We did this experiment in the Astronomy for Educators class at the university. The last time we did this, we found there's a very interesting relationship between the diameter, and I'm dropping clay on the floor now, oh no. You find out that there's an interesting thing between the diameter, and there's also a difference that has to do with the temperature of the room. Now, this can be a very nice sort of a gee whiz science demonstration for Astronomy Outreach or for a class of younger students where you don't really have to have any math. You can just say, well, why does the clay string break? Well, at some point it breaks because it's not strong enough to support its own weight, right? It's kind of like, how long can you do a dead man's hang in gym? Well, at some point your weight breaks your grip and you fall off the bar and you're done. Well, you can do this. You can stand up on a chair in a classroom and you can do this and unroll it. Or if you want to go a little bit more detailed, a little bit more into the math, you can break the kids up into groups. All right, let's each roll out a string of clay and take a card. You get your diameter, 3 millimeters, 5, 7, 9, 10, and roll your clay string out. And if you're doing this on hard tabletops, don't do it on wooden desks like mine. Ask me how I know.
How do you know?
On a smooth sealed tabletop, like Formica or a lab table at school or something that's hard, then you can roll it out. And if you're patient and careful, and you can get quite a long string. And it turns out if you're doing a 1 centimeter diameter clay string, you're going to have a ladder or a balcony or a stairwell to get enough string that this will drop. You're going to get several meters of clay string before it parts. The point is, students can go ahead, see if they can find a relationship between diameter and length. Can you find a relationship between cross-sectional area and the length? Can you find a relationship between temperature and length? That's a little bit harder to do. You have to be able to control temperature in your classroom. I suppose you could try putting the clay in an ice bath. That would work. Sure. But there's all sorts of fun science you can do, and then relate that back to how many different kinds of moons are there? Well, we know when we look at the moons of Jupiter, the innermost moon, Io, is rocky mineral moon. And as we get farther out, the outermost moon, Ganymede, is mostly ice. And the densities decrease as they go out, much as do the planets in our own solar system. And so we get these lovely, lovely interactions that tell you, gee, here's how all these things relate. And here's how moons become rings. And as the NASA video noted, rings are not permanent. If we were able to get into the amazing time machine and go back to the time of the dinosaurs, we went back before the KT impact. That would be a good thing. We went back before the KT impact. Stay out of the bushes. There are big, hungry things in there. But you could take a telescope, and at some point, if you kept going back a few tens of millennia, at some point, taking a picture of Saturn each time, at some point, you would see, bang, the rings were not there. And you could, in fact, if you had a very long-term observation program, watched the moons spiraling in to destruction and eventually, whang, they formed the ring. We believe that the impact that created Earth's moon, a planet called Theia, that's how it's referred to. Theia was roughly the size of Mars, so half the size of Earth. And if we're talking about an object that size, yeah, we can do that. We can show you what that looks like. So here's a marble representing Earth. Here's an impactor the size of Theia. That's a bad day.
Yeah.
That's a bad day. The Theia impact blasted most of the lightweight crust off of the Earth. And for a period of time, Earth had a ring of stone. These particles would have organized themselves into a ring. We don't think it was very far away. It was just outside the Roche limit. And essentially, for probably some million years or so, we were getting stadium-sized impactors from this ring falling out. But simulations people have done, supercomputers and stuff, indicate that the ring clumped up into a number of solid bodies quite quickly, within a few thousand years, a few millennia. And these bodies orbiting around crashed and solidified, and eventually we have what we know now as Luna and the large Maria.
Okay.
Well, were they asteroids from the distant solar system, or were they the last few chunks of the Theia impact recombining with our moon's surface? I don't know. It would take some serious geology on the moon's surface. You'd have to go and plan to stay a while. Come and plan, take your shoes off, stay a while. You've got some work to do. And you would have to do some very intensive mining and core sampling and stuff to even begin to answer that.
Sure.
But nevertheless, we begin to realize now the relationship between planets and moons and rings is more dynamic and more interesting and more fun than maybe we thought. Moons can become rings, and there's some indication now that rings can coalesce into moons. That happened with our Earth. And sometimes we think that moons can shred apart and recoalesce, and shred apart and recoalesce in some very violent cosmic dance. So when we talk about, can you put a moon anywhere you like? Roche says no. There's a second limit called the limit of stability, which is also attributed to Edouard Roche. It turns out not only if you get close enough do the gravitational forces between self-attraction and planetary attraction tip over to the planet wins and the moon gets shredded, but also as your moon gets farther and farther away, at some point, the gravitational tugs from the sun or from passing planets, Jupiter and Saturn are good examples here. At some point, Saturn's gravitational attraction holding a planet or a moon in orbit are balanced by the gravitational pull of the sun or its neighboring planets. And all it takes is the right tug, and off that moon goes, and it disappears and it becomes independent again. So if we think about moons, a moon around, let's say Ganymede, or our moon, it turns out, is slowly spiraling farther away. Not very fast. People argue about the exact rate, somewhere between 1 and 3 centimeters. So if you live to be 100, the moon is 1 to 2 meters farther away than when you were born. You're not going to notice. But eventually, our moon will break the surly bonds of Earth, as someone once said, and it will drift away and it will change its status from moon to planet.
To planet.
So
a question that Pekka has
Sure.
regarding this very issue. He says, is it possible that it can be captured by another planet? For instance, Mars. Could it capture the moon?
It could be.
Yeah.
More likely Venus than Mars. Venus would require falling into the gravity well toward the sun.
Okay.
And Venus is as large as the Earth is. For Mars to capture an object as large as the moon, virtually impossible. It would have to be this miracle 1 in a billion scenario where it would go into a big elliptical orbit and eventually it would circularize. Our moon is half the size of Mars. Capturing an object in orbit half the size of you is hard.
Yeah.
Pluto did it. Pluto and Charon had about that relationship. So we've got, let me see here. Can we do this? Yes, we can. So if we had Pluto and Charon, this is the relationship between Pluto and Charon. Also between
Okay.
Mars and Earth, if you want to know. So about half the size. And we think that Pluto and Charon were created when a giant impact basically split them apart and they formed two bodies.
Right.
And all the other minor moons are rubble from that collision. Probably
Now they orbit a
yes,
center.
they are. Pluto and Charon are essentially tidally locked to each other as they
Yeah.
spin. The same face of Pluto faces Charon, and the same face of Charon faces Pluto at all times. They orbit in about 6.2 days. So they just spin together, and their barycenter, their point of rotation, lies in space between them. It's actually not inside Pluto at all. Earth's barycenter with the moon is about 1% of our mass. Our barycenter is deep inside the Earth.
Mm-hmm.
So you can say that, oh, the moon and Earth, not really a binary planet, although they're very close in size. But Pluto-Charon really is a binary planet because the barycenter around which they orbit lies in, it isn't one of these things. It isn't at all. It's basically the two of them orbiting as if they were on a stick with one at each end and spinning around in a common point that's out in space between them. So, yeah, we've got all these interesting things. Moons are not forever, nor are rings. So what we're going to explore next time when we get together, Scott, we're going to take a look at the moons of Mars.
Okay.
Because the moons of Mars, Phobos and Deimos, they are doing something very, very interesting. One is being flung away farther and farther and farther. The other one is spiraling in, doomed to die. And we'll talk about which one does which, what their eventual fates may be, and some interesting science that we're hoping to do in the next decades. I hope I live to see it. We want to land and take some samples from these moons and see what we can learn of their geology.
Sure.
But we're going to go back to the idea of tides next week, because not only does a moon create a tide and affect the planet, but it also works the other way around. The tide the moon creates also affects the moon and prevents it from having a long-term stable orbit. So we'll explore that exciting adventure in our third of our planets and moons theory next week when we look at the moons of Mars. Doomed to be lost, doomed to die, but both doomed in fact. So it's kind of, it has an appropriately macabre title since they're named Fear and Panic, right? Well, why Fear and Panic? Because they're doomed, that's why. And so we'll explore that next week.
Let's see, other comments here. There's Ben Crosswaith wants to know, so does Saturn's rings rain diamonds onto the planet?
No, they're mostly water, methane, and ammonia ice. So, and those things it would be a heck of a meteor shower all the time because you would have this constant supply of effectively meteoric material. And we know that when a meteor strikes the Earth, it doesn't matter if it's carbon, stone, metal, or ice. They all have the same fate. They burn up in the atmosphere. And Saturn's atmosphere is far muddier than ours, many times, hundreds of times thicker and denser. And so these things would all burn up. You would have to have a nice floating platform somewhere just above the cloud tops. And Saturn wouldn't be particularly nice there. It would have a gravity, about 3 gravities, I think, at the cloud top. So you would not want to be dancing, but you would want your nice zero gravity chair to support your weight. But if you had some sort of a platform, you could actually observe particles, meteors every night and in abundance.
It'd be very cool. Cameron Gillis wanted to comment. He says, I just wanted to say that Dr. Barth, I really appreciate your very interesting and informative sessions. Very enjoyable, even now as I'm multitasking with my work.
So does your boss know you're taking time out to watch How Do You Know? We're glad you're here, Cameron, and really,
We're not going to
thank
call
you.
you your boss, okay?
Yeah, thank you. I'm
Let's
not calling
see.
your boss. Thank you for making time for us in your busy schedule, and I appreciate if you're understanding it and it sounds comprehensible. That's the highest compliment you can give a teacher.
Yes.
That makes sense. I understand it now. That's like the gold star for teaching. Of
Right.
course, the other end of that spectrum is, what the heck are you talking about? I don't get it. This sounds dumb. Does anybody understand it but you? Yes, I've gotten all of those comments too, but I appreciate yours even more because of
Well,
it.
that's cool.
Uh,
Daniel, no, you're on a great streak of showing us program after program, helping us understand our solar system, basic concepts that were laid down by Newton and many others. But isn't it amazing how, just brilliant some of these people were? They had to, in many cases, they had to invent the math. They had to,
they were making their tools and making it up as they went along.
Yeah.
I always taught astronomy and physics with an history of science approach. You can present the math and here do some word problems, and that's rather dull. But these people were all characters. They're interesting. They're fabulous. There's madness, mayhem, all sorts of funny stories and original ideas and conflicts and even duels. We know that Kepler, not Kepler, but Tycho Brahe, Kepler's mentor, famously fought a duel.
Didn't he have like
a silver
nose or
yes,
something?
He had a silver nose prosthetic, which he held on with coagulated goose fat. Oh. And there was no surgical adhesive at the time. And God help the man who smiles, like Cyrano de Bergerac. His nose, monsieur. Do not comment. And God help the man who smiles. Edward
coagulated goose fat.
Yes.
It wasn't even wax, right?
He had from a painting, he had a silver nose cast, pins inserted into it that protruded from the nose, and he had 2 holes drilled into his sinuses, and the pins fit in, and he put on his face every day. And he was an irascible fellow and close to the king and quite the duelist. Don't smile at Monsieur's nose. That's just not the
That's a no-no.
It's a no-no. I don't know if I would make that comment either. But he was a brilliant man. He was certainly, by many standards, a madman. But he was crazy genius.
Yes.
So I don't know. Maybe I'm not crazy enough to be a genius. I just like being a good teacher. But have I done crazy things in the classroom? Oh, yes. Anyway, so thank you all for your comments, and you're welcome to write to me, astronomyforeducators@gmail.com. And if you put in any search engine, you put in Astronomy for Educators, the Astronomy for Educators book will come up for you. And that's free to everyone, published by the University of Arkansas Library Press as an open educational resource. I'm hoping to do an update of it sometime this summer. And I'm hoping I can put links in for some of these videos that will help people as they go through the book. Hope to see you again. I hope you will like our Facebook page for How Do You Know and Explore Alliance. And please tune in next time. Share the videos with your friends. There is an Astronomy for Educators Facebook page. I always link these programs immediately after the show's over and put in other tidbits and fun things as well. So I hope you'll visit me soon. And thank you all for your attention, for your time out of your busy day, and for your comments. And don't forget, get some clay and see how far you can stretch it before it tears apart. So that's always fun. Thanks, everybody.
That's great. That's great. I wanted to just take a moment here to tell everyone tomorrow will be our 50th Global Star Party. We have a great lineup of speakers. Dave Eicher joins us back again after taking a short hiatus. Stella Kafka from the AAVSO will be on. Of course, David Levy, Libby and the Stars, Cesar Brolo, Maxi Filares, and a lot more to come. And Explore Scientific will be giving a special door prize because it is our 50th, which will be something you're going to want to win. So anyways, thanks
Autographs.
everybody. Thanks for tuning in. As my good friend Jack Horkheimer would say, keep looking up, and we'll talk to you later.
You all.
Bye-bye.
Thank you for your time, and love having all our viewers here.
Yeah.
Thanks, everybody. Have a great week.
Thanks. Hello, everybody. This is Scott Roberts from Explore Scientific. And today I want to talk about the world famous Galileo Telescope Kit. This is a kit that you assemble by yourself. You'll learn how optics work by assembling the objective lens and also the eyepiece. And there's two different eyepieces that are in this. It's a 25 power, 20 millimeter eyepiece, but it also comes with this very clever little device here that works both as a Barlow lens that will double the magnification of this eyepiece, making it 50 power, or it can be used also as a Galilean eyepiece, which gives 17 power to the telescope. This is what Galileo virtually saw through his own telescope. So you can have that same experience that Galileo had looking at the moon, looking at Saturn's rings, looking at Jupiter. It is a telescope that was designed for the International Year of Astronomy in 2009. And it's a fantastic kit, both for child and adult, to learn how a telescope works. And so if you get the telescope like this, you can either have it on a stand like this, you can hand hold it like a pirate's glass, or on the bottom here, we have a threaded hole here that you can put it on a camera tripod. Very versatile, very rugged, and a lot of fun, all from Explore Scientific.